Yeah. Okay. So then that means we can go for 10-15 moments without running from the camera. Okay. Oh, I'm sorry about this. Shit. Anyway, I apologize to people on the camera. We've got to put the camera on most of today's lectures. So lectures not recorded. Okay. Yeah. Okay. Good. So you see, it's a measure of the consistency of this picture. It's a measure of the consistency of this picture that this we get 2 pi times r2 prime times an integer. It could have gone any other way. Would have respected periodicities of the problem. Okay. So we learned something. We learned that a configuration of a D-brane wrapping a 2 torus, 2 brane wrapping a 2 torus with m units of flux maps to a 1 brane which wraps in the direction in which you haven't linearized one time to the direction in which you have linearized m times. This winding spiral times D1 brane configuration. Is this clear? Okay? Now that we know this, let's compute the energy of this configuration. This we can easily do because the energy of this configuration is simply the tension of the D-brane. Okay, is simply the tension of the D-brane times its length. Okay? So we've got some unknown factor which is the tension of the brane. We've not yet determined it. So you've got E1 times its length. What's its length? Its length is square root of 2 pi r1 of the thing squared plus 2 pi m times r2 prime. The whole thing squared. Pythagoras is here. Okay? Now this we want to rewrite in terms of so now let's undo all of this. Okay, so this is okay. So let's undo all of this in the following sense. Let's write this as this is 2 pi r1 the whole thing squared plus 2 pi m by alpha prime by r2. We want to go back to the variables of the original thing. The whole thing squared. Okay? And where was the formula for the flux? The formula for the flux was F was equal to 1 the flux was m by so m we write in terms of the flux. So this is 2 pi r1 r2 squared. So we get sum over 2 pi r1 the whole thing squared. Okay, plus f times 2 pi alpha prime times 2 pi alpha squared times 2 pi r1 whole thing squared. Okay? So now we take the 2 pi r1, the whole thing squared out common. And then there's the t1. So that I'll take it outside the square root. That's 2 pi r1 times t1. We get 1 plus f 2 pi alpha prime, the whole thing squared. Okay? Now you remember we worked out there's an extra Extra what?
Extra alpha prime?
Yeah.
How does the dimension work out? F equals 1 over L square, alpha prime equals L square. Yeah, it does work out.
Okay? Yeah. Now,
Oh, there should be an alpha prime square there.
where?
The only, no, not in this calculation. The previous.
There's an alpha prime. Oh, you're saying in the bottom side, you have the maximum side.
There should be 2 pi alpha prime square.
This is F.
Okay, just F. Okay, fine.
Yes. Okay. Now you see, this is the part that's going to give us just the tension of the plane. Okay? So the relative factor coming from the tension of the plane has the square root of 1 plus f 2 pi alpha prime in the plane square. And you can easily verify that that's what you get from this determinant if you looked at a matrix that was 1, 1, f1, 2, f1. There's a 2 pi alpha prime. This is f21 minus, yeah, so minus f1. Okay, this determinant will give us this minus this thing, the whole thing squared. Sorry, plus this thing, the whole thing squared, and then we have a square root. Okay? So basically, you see any constant f configuration can be rotated to this blockwise off-diagonal configuration by choice of the basis, which is basically the statement that any antisymmetric matrix can be brought to canonical form by rotations. So, for every such configuration, this two-brain argument works and determines the action. Okay? So we've determined that the contribution of this is an exact everything we've done here has been exact. Okay? So we've determined that the contribution of the field strength, relative to G must come in this structure. So the state duality argument, we used, the symmetry argument that determines the square root G factor, and then that becomes the square root of G plus 2 alpha prime F is determined by T duality in every single. Okay, I have one last question to you people. Out here we got T1 times 2 pi R1. Okay, but we would have expected a T2 times 2 pi R1 or times 2 pi R2. It's the area of this thing times the. How's that going to work? This is what we did last class. Where are we going to factor R2 from?
But it will come from the 5 to 5, right?
Exactly. This whole thing also has an e to the power minus phi in it, and phi changes underneath. So this was T1 times e to the power minus phi 1 times 2 pi R1, but moving to phi 2, the T duality, the diphthong before T dualizing, and then using the relationship between T1 and T2, okay, it will make us 2 pi R1 R2 times 2 pi R1 times 2 pi R2 times into e to the power minus phi. Yeah, so as Logan said, that part was guaranteed to work, because we've already worked it out. So it is a relative part that was of interest. Okay, great. So that's nice. So we determined another element of this formula, the fact that you get this determinant of GAG plus 2 pi alpha prime, in this combination. Now, there's a third element that we want to understand. What's this B doing? Okay, this is also something good.
It should be there because what is winding here becomes what is flux.
Good. That's a good physical way of thinking of it. But let me give you a very precise way to think. There's an interesting invariance that I have to introduce you to. This is my operator. Okay? And that goes as follows. Look. As you know, in space-time, we have invariance under the gauge transformation. B goes to B plus B lambda. Well, lambda is 1. Okay? Now, what I want to try to understand is how this invariance works at the level of coordinate strength. Okay? So let's remember what the action involved, what sigma model action for the B field was.
The DB action is not invariant in this.
Exactly. It will be this lack of invariance that will fix it. I got it. It's to tell us that F also transforms. I'm not going to do this. This is precisely what we're trying to address. Okay? So, look, the sigma model of the worldsheet of strength, as we've seen, couples the B field like this. Where I've just written this in geometric notation. The integral of B over the manifold of that the string space traces out in space time. We've written this in indices last time. P mu nu, del alpha x mu, del beta x mu, epsilon alpha beta. That's the invariant. There's a thing. Okay? And if we were looking at closed string theory, the shift of B goes to B plus D lambda does not change its action simply because D lambda integrates to 0 over a manifold with no boundaries. Now let's work with open string theory. Okay? When we work with open string theory, what happens? What we get is that under B goes to B plus D lambda, this object changes D lambda. So it becomes 1 by 2 pi alpha prime integral of lambda. Over the bound. But how does A, you see, the integral, you remember what the vertex operator for the A field is? Yes, the vertex operator was del Tx. Okay? Del Tx mu. And so the coupling of A to the boundary of, so firstly, A being a vertex operator that lives only over, that's described in open string theory, lives only on the boundary. So vertex operator localized on the boundary. Okay? And if you wanted to modify the sigma model of string theory to include the effect of a background A field, you will exponentiate its vertex operator. Okay? And that would involve a term that was integral of del Tx times mu times A mu on the boundary of the string relation. Okay? So let's say this again. Let's start with the worldsheet action in the presence of both B field and A field. That worldsheet action is 1 over 2 pi alpha prime times integral B plus over the worldsheet, let's call it M, the manifold M, plus integral over the boundary of M. Integral of the one for me over the boundary of M. That's exactly what this is. Okay? So, in open string theory, B goes to lambda is not by itself an invariance.
This is just a statement that the end of the strings carry the charge.
That's right.
Hence they behave like charges.
That's the
For the
yes. Exactly.
So this is just a
Exactly.
is there a particle coupling to the
Exactly. It's particle coupling. That's completely. Okay. So now let's look at what the full engagement. Is there an invariance in open string? Okay. In open string theory, there is an invariance, and that invariance comes from B goes to B plus D lambda. A goes to A minus lambda. Remember, lambda is one side. Of course, it's a factor of 2 pi, so that's 2 pi.
A equals A minus lambda is not a gauge.
It's not a gauge. In fact, under this transformation, f goes to f minus d lambda, that's 2 pi. I will put 2 pi alpha prime to the right of this. One. Therefore, f by itself is gauge invariant under the U1 gauge transformations of the gauge field. That's obvious. It's a usual story. But it's not gauge invariant under this gauge transformation. Okay? But the combination 2 pi alpha prime f plus b is gauge invariant under the one form gauge transformations coming from the B field. Is this clear? In open string theory, the A field, the field that comes from the gauge field of the gauge bosons of the endpoint of the strings, and the field strength of that is not invariant, gauge invariant. It's not a symmetric. Just this action is not symmetric. Okay? It's this combined action. Okay? So the only invariance, if you want to write down the gauge invariant, it's gauge invariant both under the U1 gauge transformations as well as the one form gauge transformations. This is the only thing. So in any formula that you have f appear, you will also have, it will appear in the combination 2 pi alpha prime f plus b. And that's this.
Just open strings.
No, right. This is just open.
Now, in the low energy action,
yes.
There's a separate kinetic term for f and a separate kinetic term for b, right? I mean, there's an f square term and there's an h square term.
There's an h square term, but the f term as we've seen from here.
Okay, but this is a. Oh. Okay.
You get the low energy vector action by expanding this.
The details all the actions.
Basically, this little manipulation of the world sheet has shown you that if there's an f square, it's actually an f minus, 2 pi f plus B.
So we can just, so in one sense, we can just say that F is just a gauge. F and A are just gauge artifacts. We can just go to gauge that F and A are 0.
Okay. You can go to a gauge where.
So it's actually the B which is, which is available. I mean the B without the D lambda. You use the gauge freedom to set A to 0, F to 0. So then you lose the ability to do large worksheet transformations on B. And so it is the B field which is that what this is?
Yeah. Let's see. You're right. That there would be a way of fixing this gauge invariance by setting F to 0. And that's right. No, it's not often. Often not. I think that's.
Basically, this two terms are just integral from B tilde, where B tilde is.
That's right. Everything in the action will appear in this combination. Every time you have an F, you will also have this B.
So you just take the closed string field and you put boundaries and you get the.
That's right. Right. If you want a two-form field with a gauge invariance, you want that because otherwise you have negative ground states. You want a gauge invariance because otherwise you have negative ground states. You'd be forced to put a gauge field on the boundary. Okay. Good. So now we've understood every aspect of this formula. We've understood the square root G. We've understood the relative appearance of F. We've understood the relative appearance of B. Okay? And just to say again what the domain of validity of this formula is. Okay? This formula is supposed to work in the leading order, in a curvature expansion of the shape of the brane, and leading order in derivative expansion of F's and therefore B's. And it's exact when F is constant, but if F is slowly varying, it's good. With terms that involve derivatives of F. As you can see from our derivation, right? We got it correct for a string that was linear. Okay, because for that we know the exact answer. Okay? We got it correct for a string that was linear, but if you have some funny varying shape, we'd have to do more calculations. Okay. And any questions or comments about this? Maybe I'll just spend 5 minutes to talk about the tension of Gilman.
There's no way of seeing this in the. Okay, this will definitely affect the Lorentz action.
Yes.
No way of seeing it in the Lorentz action.
Meaning, we write down the Lorentz effective action that's consistent with this. That's what we mean.
So there will be there will be relations between a lot of coefficients of B and F.
Yes. Naively, you wouldn't have an appearance of B at all.
You would have a H.
You would have only as D.
Yeah.
Now we've got B, not D, in the action, because I changed.
Instead of this, understanding this is just, you just take a closed string and you do something to it, to boundaries, and this F is just, the sector is just a constant boundary. The case which you get.
I mean, that's more or less what you do. You see, as you said, if you want a closed string and you want to couple consistently to a B field, you must also have coupling to.
And you cut that closed string, it better develop some degrees of freedom in the.
Yeah, I mean, if you've got a dynamical field that couples to the, like integral B, you have to have a dynamical field that couples like integral A. That's the only way of maintaining the dynamics. Okay, and now if you've got the coupling, you know everything. You know this field that couples to, as you said, like it couples to John. Okay, good. Let me just, I'm sorry, I promised to stop by 4, but I really stopped at 5 minutes. Just because the exam's coming up, and we want to finish everything. Okay. Are you happy to now continue? Okay, let's proceed. Okay, now, the last thing I will do is explain to you how you can actually use string perturbation theory to calculate the tension. Okay. So, what we're going to do is to use, I'm going to sketch it out. I'm going to sketch it out for you without numbers and so on. I'm going to urge you to fill out the details. It's all the questions. Okay. What we're going to do, you see, the main idea is as follows. You remember that when we were studying the 1-2 amplitude of an open string, we looked at this cylinder amplitude. Please.
So here we have, so this would be true of, so if we have any world volume which is coupled to some, some P-form field like this, is it true that,
if you put boundaries, I think it will be a P minus 1 form.
There will be P minus
1 form, there will be that, I think. Yeah. If you allow boundaries in that. Yeah, so that's, I think that's true, and I think there are several examples. Okay, good. So now, look. You remember that we studied the open string, 1-2 open string amplitude on in open string theory, and I'll just remind you what the final answer was. Okay, you remember what we got was this 1 over tau to the power 13. That's tau to the half to the power 26. This came, so let's say its length was t. Tau in this case was t. Okay, so we had, so let's just say t to the power 13. Good. Want to call it tau? Sorry? In tau. Yes. And then we had product of n is equal to 1 to infinity. 1 minus q to the power n, and 1 minus q bar to the power n, but q is equal to q bar. Yes, it's a straight cylinder. So we had this to the power where is it? We have this to the power 24/48. Okay, and then we had dt by t from the integral over the moduli. Right? Then we have several other factors of alpha prime and so on, which I'm ignoring just so that we can look at the structure. This is the integral, the measure of the moduli space. Okay, and we also have in each of these. We have the right power to make this an integral function. This is q bar to the power minus 1, so q squared to the power x. Okay, the 0 point energy stuff. Then, you remember we did a modular transformation of this object. Okay? And we realized that this whole thing was just eta of, was just the same object. Okay? Was this, was the same object but without the t to the 1 by 30. Written in terms of 1 by 30. In terms of the s value. Right? What do I want to say? This was simply this term. Okay. Sorry, let me say it's more systematic. We first made this square and then 12. And then we found that this object had a modular transformation property. I made it simply integral ds and then 1 over so 1 over q to the power minus q tilde to the power minus 2 over product n is equal to 1 to infinity 1 minus q tilde n to the power 48. Okay, whereas q tilde was equal to e to the power 2 pi times 1 by 2. Okay? Q tilde is equal to the power minus s. Q tilde is equal to the power minus 2 pi s. The original Q is equal to the power minus 2 pi t. It was 2 pi I tau and r, and t was I, tau and I. Okay? So this was the structure we had. Okay. This thing has a name, it has a fancy name, it's called an eta. But we ignore that. Okay. And then we realized that we could take this object and then power expand it in powers e to the power minus 2 pi s. Okay? So the first term was this e to the power 2 pi, well, e to the power 4 pi s. And then the next term was I'm sorry. This was, sorry. I'm sorry. This is not 48. This is, I'm sorry, what did I go? Sorry, just a minute. When we open string theory, we're going to get one set of oscillators. Okay? And for that one set of oscillators, we have L0 equals L0. L0 equals, let me just check, sorry. This was 24. 24. This was now 2 of minus 1, and this was 24. Sorry, we just I was doubling it. We have only one set of oscillators on the open string. Minus 1. So we have 2 pi s e to the power 2 pi s. Okay, and then a term that was this is about 24, so we get plus 24 plus exponentially that. Okay? Now, we were looking at, if you remember what we did earlier, we were looking at ultraviolet divergences of this amplitude. Ultraviolet divergences came from the region very small t, therefore from the region very large s. Okay? We reinterpreted those ultraviolet divergences as to do with infrared divergences in this closed string channel. The infrared divergence from here reflected the propagation closed string tachyon, which was, okay, we don't care about that. The divergence that comes from here was more serious. Whereas the divergence which was 24 times integral ds. And we interpreted that as having energy in all of space. If you remember. Right? The divergence that came from having the cosmological constant. Having a source for the graviton, a source for the dileton in all of space. And we discussed in detail how that leads to divergence. Okay. Now, what's the basic idea? The basic idea is this. Look, if you've got energy in all of space, that gives you divergence. But if you've got some energy density localized somewhere in space, well, that's no divergence. What you set up is some solution in which the graviton and the dileton diodes. Okay? So, if you do the same calculation for a D brane rather than for the open string, this divergence should not be a divergence. And in fact, should give you what you get from the closed string channel due to graviton and dileton exchange between two D branes. I'll leave it simple. If you get only one D brane, you get something. But what I'm interested in is considering two D branes and looking at this diagram in the 1-2 channel. In the channel where you have open strings with one end on one D brane and the other end on the other D brane.
This was not done for normal.
What?
This was done in normal direction, right?
This was so far done with only one. Now we're going to discuss how that changes if we do it with the Dirichlet directions and do it for two D branes. Okay? Now why do we want to do it for two D branes? We want to do it for two D branes because the graviton exchange between two D branes gives you the interaction energy between two D branes. Okay? You can also try to find the self energy of one D brane, but that will be plagued by ultraviolet divergences near the brane. Just like the energy of a charged particle. It's not, this way is not very good to find. So you'd have to sort of resolve it and do a detailed calculation. But the interaction energy between two charged particles is extremely well defined. No divergences. So let's try to do the same calculation here. The same calculation that we did for open strings before. But concentrate on open strings between that has one end on one D brane, the other end on the other brane. That will be the closed strings channel, a closed string that goes in a cylinder, one end of which is the first D brane, second of which is the second D brane. So it represents a string sourced by this first D brane, propagated to the second D brane. Okay? And will be exactly the analog of computing the interaction energy between two charged particles by integrating out the gate boson that goes between them. You understand that, right? Just give you the Green's function. So if we can repeat this calculation, now with the presence of two D branes, we will be able to determine how the D brane source the dileton, how the D brane source the graviton, and thereby determine the D brane tension. Now of course, well, you could actually do it even better, but that's why we determined the D brane effective action before doing this exercise. We know the full effective action. We know how the D brane couples to the dileton and the graviton up to an overall number. So this calculation is now going to reveal that overall number. Is this clear? Okay, so let's see the contour of this calculation. What changes? What changes in what we've done when we look at a D brane? So let's look at D brane that has codimension C. number of directions in which it's localized is C. Okay? And remember, we're considering two D-branes which have distance y. Okay, so there are two obvious changes in this whole procedure. The first change is that there is, remember we're working the open string set. We'll interpret the results of your string set. We're working the open string set. Every string state has extra energy because it's stretched between the two. What is the extra energy? Remember we're interested in wordsheet energy. Just evaluating the wordsheet action of the stretching. Okay? So what's the, so it's x is equal to y by sigma 1, and when sigma 1 becomes pi, we want this to be 1. Okay, so that's the classical configuration corresponding to the string stretching between two branes. Okay, and then so we have del sigma 1, del 1x, the whole thing squared, 1 by 4 pi alpha prime. What does that give us? It gives us a factor of 1 by 4 pi squared alpha prime times y squared. Okay? Now, what we're computing is e to the power minus 2 pi t times n is 0. So we get an additional factor of e to the power minus y squared by 2 pi alpha times t. Okay? So that's the first change. We have the insertion of such a factor into the subject. What's the second change? Can anyone tell me what other change we get?
Zero more.
Exactly. So instead of getting a t to the 13, we get t to the 13 minus c by 2. Right? So the only change will be in this, t to the 13 goes to t to the 13 minus c by 2. And of course we have this, and we have this additional factor e to the power minus y squared. Okay? So, then what do we get? Once we make this transformation to S, what do we get? We get a factor of, so we had an additional factor of 1 over t to the power minus c by 2, which will go to a factor of 1 over s to the power c by 2. And we'll also get an additional factor of e to the power minus y squared over 2 pi alpha primes times this power series expansion here. E to the power 2 pi s, that's 24 plus 2. Okay. Now, of course, we ignore the tachyon once again. So we're interested in this time frame. Okay? Now, what's the answer to this? This was a divergence when C was 0. But when C is large enough, it doesn't diverge. It doesn't diverge because small s is suppressed by this exponential. And when C is large enough, large s does not diverge. Okay? basically you need enough codimension to make, putting a point particle in 2 dimensions gives you these log effects. Okay? Putting a point particle in 1 dimension really changes everything. In codimension 1 really changes everything. In 2 dimensions it also changes infinity quite substantially. Okay? But in 3 dimensions, 3 codimensions, it's like 1 over r 10 to the 12. So it's physically expensive. So as was said, the C greater than 2, codimension greater than 2, this thing is finite. And what's the answer? We can get the answer by power transfer. Right? Because the answer then is the net power is just 1 over s to the power c by 2 minus 1. But s dx by y squared. Okay? So we get 1 over y squared to the power c by 2 minus 1. So the answer is 1 over y to the power c minus 2. Times numbers that one should look up. Alpha, we're not keeping time alpha pattern, in fact pi. I just want to show you the structure, the dependence of the distance. I'm going to ask you to work this out carefully with all factors yourself. Now, if you think about this is a perfectly reasonable answer. Why is this a perfectly reasonable answer? Because this is the dependence of the Green's function of del square on y in a c-dimensional space. 3-dimensional space, del square is 1 by r. In a c-dimensional space, del square is 1 by y to the power c minus 2. It's a resulting by power. Because the Green's function. Okay, so this is exactly the result that you would expect for the interaction energy from the exchange of massless particles between 2 point-like objects in c dimensions, c spatial dimensions, separated by distance y. So the y dependence works out okay. Okay? So, you have to do 2 things. The first thing you have to do is to do this calculation carefully, keeping track of all the prefactors. The next thing you have to do is to take the Born-Enkelt action we worked out before. Okay? And calculate the interaction energy between 2 d branes separated by distance y from graviton and dilaton exchange. We know how the graviton and the dilaton couple to d branes.
We can just talk with the 2 derivatives. Do we need to put...
No. But it's important that you have the relative coupling of the graviton and dilaton. You're going to expand this to quadratic order, to linear order of class, basically. This is just the source. That's all you get. Okay? And then solve for the interaction energy coming from the exchange of the graviton and the dilaton. The answer, of course, is going to be proportional to Green's function. You just have to get the normalization. Okay? So what's the structure of what you have to do? You get p squared times 1 by y to the power c minus 2 times some numbers is equal to some other numbers, which when you do this calculation carefully, divided by y plus c minus 2. This cancels. So when you work out those numbers carefully, you get the answer for the tension of the beam. I want you to sit and think for a moment how clever this is. You see, because when we worked on the rules of string theory, in general, at every step there were various normalizations we had to keep very careful track of. Okay? So, for instance, if you try to calculate the tension of the brain using by computing the 1-point function of the graviton, you would have to be very carefully think through all issues of normalization. However, what do we use here? We use the one-loop amplitude of open strings. A one-loop amplitude is a trace. And traces have no undetermined normalizations. This whole formula that we obtained was to take the trace It's just sum over the spectrum of the e to the power minus beta h. We know the spectrum of the theory, so we can calculate e to the power minus beta h. So the one loop amplitude in the open string sector had no undetermined normalization issue. And that one loop amplitude is simply the energy obtained from closed string exchange between two lead brains. In the closed string exchange between two lead brains, that's a normalization issue, but that's just the tension of the lead brain that we would define. So the first part of the calculation, the string calculation, was entirely normalization free. No normalization between. That's why we're doing this. You can also look at the 1-point function of the parameter, but we have to be much more careful with normalization. Okay? Now, when you work this out carefully, you get the following answer. You get t0 is equal to 1 over square root alpha, right? You go to pi's. And in fact, Tp is equal to 1 over g, sorry, and 1 over g alpha prime to the power of p plus 1 to pi to the power k. I hope I got 2 pi right. Which just gets this horrible habit of writing all these normalizations in terms of the 10-dimensional gravity, Newton's constant. And, you know, to trace through the answers in terms of alpha prime and g is generally 1 hour's work. So, he just does not most straightforward version. I think this is right. Once you check it against the paper, this is what I got. We have got 2 pi. Yeah. The field length is what we got. It's just a question of whether I got T0 right. It was 2 pi, a little bit. But anyway, we look up, there's many classical numbers. And of course, you can work it. Okay, great. Okay, so now we know how to calculate the tension. Okay? And you see that this business about ultraviolet of the open string becoming ultraviolet of the closed string and so on. You see, all that stuff that you were, especially Jyotirma, was very worried about in the interpretation. It's not just fictional jazz. It's true and it's useful for computation. You see, the same thing that explained it. You see, you remember we said that the explanation of the divergence of the open string amplitude was that there was energy over all space. And that gives you a divergence. Okay? When we regulated this divergence, that is, we put the energy not over all of space, but on some submanifolds, we got no divergence. In fact, we got a physical answer that helped us find the tension. So that interpretation isn't just for fun. It's really true and it's useful. Okay, I think that's all I wanted to say today. We've completed our discussion of chapter 8 in Brzezinski, apart from the discussion of oriented folds. Okay? Now, oriented folds, I personally find a painful topic, but we'll discuss it. No, my suggestion is that we first discuss strings moving in curved space because it's much more fun. Okay, so next week we have a class on Wednesday. No class on Friday, no class on Wednesday after that. Then we have a class on Friday again. So for the next 2 lectures, we have a thorough and enjoyable, hopefully enjoyable discussion of the propagation of strings through curved space. And our last lecture of this semester before your exam, we'll talk about oriented folds. Okay, and that will be the end of our discussion of the material in Brzezinski chapter 1, or volume 1. Okay, that's it. I'll answer the questions. Okay?